All right, so we're introducing today the concept of the antiderivative, okay? Now, those of you who know your prefixes, what does anti mean? Against, yeah, against, or opposed to, or opposite of, all right? If you are anti something, you're against that. Well, this is the antiderivative. It's kind of doing the backwards thing of what a derivative does. Okay? Now, it's not exactly an inverse. It's not an inverse, as we'll see later on. Okay? However, logically thinking through, this is kind of what we're dealing with. Okay? We've already worked with these derivatives. F prime of x is 2x. F prime of x is x. F prime of x is x squared. So I want you to think logically here and try to tell me, okay, if the derivative was 2x, what would the original function have been?
X squared plus something.
Okay, it's x squared. All right?
Plus yes.
Some people have been working ahead a little bit, huh? Okay, why are you saying plus some constant? What?
Its power is 0.
Okay, its power is 0 for x, so when you do the power rule, it's 0 times whatever, so it ends up being 0, right? So if I took the derivative of that constant, it'll be 0. So you're actually kind of picking up on the idea here that there's actually more than one answer to this, right? It's x squared plus 5, or x squared plus 8, or x squared minus pi. All right, as long as that's a constant, when we take the derivative, it'll be 0, okay? So, and we can check ourselves with this. We could even say, okay, what's the derivative of x squared plus a constant c? Well, it's 2x plus 0, which is just 2x. All right, so it worked. What would if the derivative equaled x, what would the original function be? What function has a derivative equal to x?
X as is it x to the power of x?
No?
1/2 times x squared.
Okay. We need an x squared to get down to an x to the first, right? But as we already said, x squared gives us 2x. So good. Terry picked up we need a half here so that when we take the derivative, 2 times a half, if we're taking the derivative of 1/2 x squared, it's going to be 2 times a half, which is just 1x. Okay? All right. Let's do one more here. If we had x squared as our derivative, what would the original function have been?
1/3 x cubed.
1/3 x cubed. The 1/3 is there to counter when you're multiplying by the 3, so you get a coefficient of just 1 again. Okay, so if we took the derivative of 1/3 x cubed, we'd have 3 times 1/3, which is just 1 x squared. Okay? You guys getting the hang of this a little bit?
Yes.
Okay, good, good. So take a couple minutes here. I want you to try to figure out these last 3, okay? All right, do we have some ideas?
Yes.
Okay. So what'd you get for 1/x squared?
Negative x to the negative 1.
2x.
Negative 1/3 x to negative 3.
What?
Negative 1/3 x to the
Wait.
negative 3. Is that what you said?
Wait,
X power is x.
Well, let's test it out, okay? Negative 1/3 x to negative 3, okay? So negative 1/3 times negative 3 is, okay, negative 1/3 times negative 3 would be 1, right? And then if I took the derivative of that, that means x would now be to the negative fourth, okay? So our power's a little off there, okay? Negative 1 over x,
Yeah, that's what I said.
okay? Well, let's try it, okay? Let's try it. Negative 1 over x, which is negative x to the negative 1, right? So negative 1 times the negative 1 is positive 1, right? And then we subtract 1 from the exponent, so it's now x to the negative 2. That works. Okay? Good. All right. How about this next one? If it's 1 over x cubed.
Negative 1 over 2x squared.
Negative 1 over 2x squared. So you're saying a negative 1/2 x to the negative 2, right? So that's the same thing. So if we multiply negative 2 times negative 1/2, that's positive 1. Subtract 1 from the exponent, it's x to the negative 3. 1 over x cubed. That works. Okay? Alright, so then we have cosine. The derivative of what equals cosine? Sine. Yeah, that one's a little easier. Okay, so sine of x would be the original function. Alright? Now, we're figuring that out logically. We're going to look at some rules here in a minute on that you're going to need to memorize basically in order to be able to just write down the answers to these. However, I want to take a step back and look at this plus c, because every one of these could have the plus c on them. Okay, because the derivative of any of these plus a constant would be the same thing. Okay, and you'll notice here I have this diagram right over here. What would it look like if this is my f of x and I have a tangent line here that has a slope of 2/3? What would happen to my graph if I added a constant to the end of it?
Add a positive or negative.
Where it doesn't matter. It would shift which way? Vertically, okay? It would shift vertically. So guess what? If I did f of x plus some constant c, and it moved down to here, okay? Almost identical. All right, if it moves down to there, and I have at the same value of x, I took the tangent, what's the slope of that line going to be?
2/3.
Yeah, the slope of that tangent will also equal 2/3. Okay? And really what's happening here is this is what I'm doing here when I'm illustrating the idea of that plus c, and why the derivative would be the same regardless of what constant I add on to the end here. Because what happens is a vertical shift will not impact the slope at a point. Okay? A vertical shift will not impact the slope at a value of x. Okay? And the reason for that is because the derivative of a constant is 0. Okay? So, that's just another note here I wanted to make about that plus c. Okay, now that plus c should go on the end of every one of your answers when we're doing these antiderivatives. Okay? So, let's actually take a step here and look at one quick application. We have what's called a differential equation. You'll see here it's an equation involving y prime. Okay? So if y prime equals 2, what would y equal?
2x plus c.
Yeah, 2x plus whatever constant we wanted. Okay? 2x plus c. So, let's take a quick look here at some notation. Alright? And it's notation for the antiderivative, okay? An antiderivative, we often will use this capital letter for our function, okay? Capital F of x is an antiderivative of f of x if this is true, okay? It's the antiderivative if the derivative of capital F of x equals f of x. Okay? This is the antiderivative of a function if its derivative equals the function.
So there can be infinity. There can be infinity antiderivatives.
That's correct. There are infinite antiderivatives because that plus c means that it could be anything. All right? And that actually brings us to a theorem here.
Wait, Mr. Hickson,
Yes.
if you're saying f of x is the antiderivative of f of x, are you saying that capital F of x is equal to capital F? Wait, I'm a little bit confused.
This is an antiderivative of f of x.
So f of x is the derivative, and then it's capital F of x is the function.
Yes.
Okay.
Okay? Yeah, the little f of x is the derivative of capital F of x.
Oh, right. Isn't that, yeah, okay.
Yeah. Okay? So here's a little theorem that we could work through here. If capital F is an antiderivative of f on an interval I, then capital G is also an antiderivative of f on the interval I, if and only if capital G is in the form capital G of x equals capital F of x plus c for all x's in the interval where c is a constant. Okay? Let me walk you through what we're talking about here. Okay?
What is IFI?
IFF stands for if and only if. Okay? If and only if. That means the first half is only true if the second half is true, but also it works the other way. The first half is only true if the second half is true. Okay? We call this a biconditional. Alright? If this is true, then this is true, but also if the second part is true, then we know the first part is true.
So one of two parts is true, then everything is true.
Then the other part is true automatically, yes. Okay? Alright, so let's look at this notation here real quickly, and then we'll prove this, okay? The notation that we have, and really what we're doing, we don't want to talk about taking derivatives of stuff anymore. We want to be able to find the antiderivative, because now we're not going to know the function that we want to take the derivative of. We know the answer. We want to go backwards to get the original function, the antiderivative. Okay? So, notice the notation here. We have this elongated s. Alright, that's the integral sign.
Yes.
Yeah, Leibniz took an s and he stretched it out like this. Okay, because as you guys will see later on, the integral is just a big sum. So he took the s from sum and stretched it out and made our integral symbol.
He's so small.
Okay? So, the integral of a function, integral of f of x dx, equals the antiderivative plus any value of c. Okay? That's what this is saying. We would read this as the integral of f of x dx is the antiderivative of f with respect to x. That's what that dx stands for. It's just like when we were doing dy dx for derivatives, the dx on the bottom told us what we were differentiating with respect to. Okay? The dx here tells us what we're going to integrate with respect to. Okay? The differential dx serves to identify x as the variable of integration. Okay? Now, let's look at a proof of what we're doing here.
Can you do an example because I feel it's kind of abstract for me to understand?
Yes. Yeah. So, we're going to work through a few examples down here at the bottom, but this proof I think will even help as well. Okay? If f is the antiderivative of f, that means that the integral of f of x dx equals capital F of x. Okay? Plus c. Okay? Now, if it's an antiderivative, by definition, what we set up there is that the derivative of f of x is going to equal f of x, right? That's the definition we gave right up here. Okay? However, let's say that I take the derivative of g of x. Okay? Well, g of x is simply f of x plus c. According to our theorem, g of x is f of x plus c, right? Well, if I'm taking the derivative of a sum, I can just take the sum of the two derivatives, right? So, I have the derivative of capital F of x plus, what's the derivative of c? 0. So that equals capital F prime of x. And that proves that as long as g is in this form, okay, as long as g is in this form, it will also be an antiderivative. Okay? Now, we're going to get into some basic integration rules. I'm going to give you a big list of them, but then we're going to try using a number of them. And we'll refer back and forth to them, okay? So, basic integration, if you take the integral of the derivative of a function, that will give us the original function. That's kind of just what we were saying. We're just using different notation. We're substituting the derivative of capital F of x in here. Okay? And then we can see how integration is the quote-unquote inverse. It's not exactly the inverse because that plus c gives us multiple options, but it's kind of the same idea. And because of that, we can see this. If you take the derivative of the integral, it will take you back to the function you started with. So the derivative with respect to x of the integral of f of x dx, or I should say the antiderivative of f of x dx, will equal f of x.
So it'll always bring you to a parent function?
It'll always bring you to whatever the original thing inside the antiderivative was.
But it won't have any shifts or translations, it'll just be the parent function of...
Yes, it'll always just be that function. You won't put a plus c in this case because when you do the integral inside, you have a plus c, but then if you take the derivative of that, the c is now 0. Okay?
So is it saying if you take the derivative of capital F prime x, it's equal to f of x?
If you take the derivative of capital F of x, it will give you f of x.
Okay.
Yes.
Oh, yeah.
Okay? All right. So here are a bunch of rules. Let's zoom in here a little bit. we got a number of rules here, and these are rules that you're simply going to have to memorize, okay? The integral of 0 is a constant, 0 plus c, okay? The integral of k, well, think about it. What had a derivative that ended up just being a number? Well, a line did. So that's how we have kx plus c, okay? A line has a slope that's constant k. So, going the other way now. The rest of these basically are just memorizing. You'll notice a lot of similarity between the derivatives we learned. Okay? One that I want to isolate though is this one right here, the power rule. Okay? The power rule. It says the integral or the antiderivative of x to the n dx equals x to the n plus 1 over n plus 1 plus c. Okay? Can someone put in their own words what's going on here?
Divided by the power.
You're dividing by a power.
No, the same power, like x to the 5th over 5.
Okay. You end up dividing by the same number that x has now as an exponent. Okay. Good. So notice here we're going to add 1 to the exponent, and then we're going to divide by the new exponent.
Isn't that just the opposite of the power rule?
It basically is. Yeah, if you think about the power rule for derivatives, you multiplied by the original exponent and then subtracted 1. Here, you're adding 1 first and then dividing by the new exponent. Okay? So add 1 to the exponent. And then divide by the new exponent. Okay? So, let's do a couple of these real quickly. The integral of x squared dx. Using the rule here. The integral of x squared dx.
1/3.
Okay? Add 1, so it's x to the third. Divide by 3, or 1/3 times x cubed. Alright? And then, of course, plus c. How about the integral of x to the negative third power dx?
Negative x to the negative 2 over 2.
Okay? Yeah. It's a negative x to the negative 2 over 2 plus c. And just like with derivatives, it'd be good for you to go ahead and simplify. So it'd be negative 1 over 2x squared plus c. Okay? Now, you'll notice here this has an extra part to it that wasn't with the derivatives. And that's what that n cannot be negative 1. Why would that be?
Because when you divide by 0, or when you plug n in, it gives you 0.
That's right. If I add 1 to n, I get 0, so I'd have x to the 0 divided by 0, which is undefined. Okay? We will learn later on a different rule for when we're trying to take the integral or the antiderivative of 1 over x. Okay? So let's work through a couple of examples here. Okay? We're going to rewrite or describe the antiderivative. Okay? We're going to rewrite, though, before integrating. So here, what rule are we using? Huh? We're going to use the power rule by rewriting this as x to the negative 3. Okay? Now we can actually integrate. What is it? Come on, guys.
X to the negative 2 over negative 3.
Thank you. We literally just did this one. All right. Okay. And then, of course, always simplify. Like we said, it's going to be 1 over 2x squared plus c. Okay? All right, so the next one, what rule are we going to use? Power rule again, because we're going to rewrite this as the integral of x to the 1/2. So, what's the antiderivative of x to the 1/2? X to the 3 over 2 over 3 over 2. Good. And we simplify. What's that going to simplify to? 2x to the 3 over 2 over 3 plus c. Okay? Is this making sense? Are we understanding? Some of you aren't really engaging here, I don't think, and it's going to show later. Right. Okay, so now the integral of 2 sine of x dx. What rule are we going to have to use? We don't have a chain rule for integration.
Power.
This is just a constant, right? Constant multiple. So that's actually the same as 2 times the integral of sine of x dx. The constant multiple rule is up there. It's one of the ones we have in our list. Okay? If you have a constant times a function, you can pull the constant out and just take the integral of the function. So what's the integral of sine? Negative cosine. So we got a negative 2 cosine of x plus c. And that can't be simplified. Okay? Let's take a look at our next set here. The integral of dx.
X plus C.
Okay?
C.
Yeah, X.
1 equals C.
Are we taking, when does it equal c?
Do you put the constant?
Well, when it was 0. Are we taking the integral of 0? No, there's an understood 1, right? So, Terry, you're right there. It'd be x plus c. Okay? X plus c. You could even think of it as the power rule. Right now it's 1x to the 0 power. I add 1 to the exponent, so now it's x to the first. I divide by 1. Okay? It's still x. Alright? How about b?
1/2 x squared
Okay, 1/2 x squared
plus 2x plus c.
plus 2x plus c. Okay? Yeah. Alright? And c. 3x to the 4th minus 5x squared plus x. 3x to the 5th
And
over 5.
3.
Good. What is it? X squared over 2. X squared over 2 plus c. Okay? Plus c. Here's a little test-taking strategy. If you're asked to get the antiderivative of something and you have no clue, at least put something plus c. Okay? You'll at least get the point for plus c. Alright? So,
Something plus.
okay. Alright, so now we have these types of functions. Just like we did when we were doing derivatives, we started getting more and more complex functions. And some of these we have to simplify before we're able to take the integral. Okay? So, for a here, if I'm doing the integral of x plus 1 over radical x dx, how am I going to get that in a form that I can take the antiderivative of? Okay, so x plus 1 times x to the negative 1/2. Now, we don't have a product rule in integration. So what are we going to have to do? Okay, we could distribute it. So what's x times x to the negative 1/2? X to the 1/2. And then times 1, so it's plus x to the negative 1/2. Okay? And now we have it in a form that we can integrate. So the integral of x to the 1/2. 2/3 x to the what? To the 3/2, okay? Alright, so you add 1. You might want to write down x to the power first. So it's x to the 3/2, we add 1. Then you divide by 3/2, which is the same as multiplying by 2/3. Okay? How about the x to the negative 1/2? It's going to be x to what power? 1/2. And what are we multiplying that by?
2.
Times 2. Yeah, it's divided by 1/2, which means we're then times 2. And good, plus c. Okay?
Wait, how come you did the,
Trying that.
okay, so you take x and you multiply it by, well, you keep, just add 1 to the exponent, right?
Yeah, so here we add 1 and then divide by the new exponent. So you're dividing by a fraction, we flip and multiply. Same thing here, x to the 1/2 divided by 1/2, flip and multiply, and you get 2. Okay. Alright, now this one, the trig one here at the bottom, you have to think a little bit, and think about those rules that you have up on the previous page. Okay? How can I get this to look like one of the rules we have on the previous page?
Sine x times cosine square x over 1. I mean 1 over.
Okay? So this right here is sine times 1 over cosine squared.
Then negative. It's negative. And negative.
I'm sorry, what? Look back at the rules that we had in the previous thing, or you can look at those kind of backwards that I have written on the board. Okay, a secant, that would be a secant squared times sine, but we don't have a rule for secant squared times sine. We do, however, if I put one of those cosines underneath the sine instead of underneath the 1, what am I taking the integral of? Secant times tangent. Okay? And what's the integral of secant times tangent? secant. Okay? So see, the better you know your derivative rules, actually, it helps you with these integral rules. Okay? Alright, so the final thing we're going to end with here, we won't get through all of these, but that's okay. Initial conditions and particular solutions. You might be like, well, what in the world are they talking about here? Okay? We have, in this example here, we have the integral or the antiderivative of 3x squared minus 1 dx. Okay? And you guys, at this point, we're getting pretty good with these polynomial ones. It's going to be 3x cubed over 3, so just x cubed, minus x plus c. That's our general solution, our general antiderivative. However, if we are given a specific point, you'll notice here this graph shows us all the different, or not all, but a lot of the different values of c. Here's x cubed minus x right here in the middle. Okay, right here. Okay, and that's where c equals 0. Okay, but then if c equals 1 or 2 or 3 or 4 or negative 1 or so on, all of those are possibilities. So, if we know one value of that antiderivative, okay, if we're given 1 point, then we're able to figure out what c is, okay? So let's take a quick look at this. Let's say that I told you that the point 1, well, let's make it 2, 10, okay? Let's say the point 2, 10 is on the graph. Okay, of the antiderivative. Okay, so what I would do here is I would simply take, okay, this is our antiderivative, or we just need y. Okay, so 10 is going to equal 2 cubed minus 2 plus c. All right, so 8 minus 2 is 6, 10 minus 6, that means c equals 4, so now I can say exactly what the original function is, exactly what that y is. That y is, in this case, x cubed minus x plus 4. Okay? That is the particular solution if this point is on the antiderivative. Okay? And you could do that with any of these functions if you know 1 point. Okay? If I know this one and I know that capital F of 1 equals 0, well, I would take the integral of 1 over x squared dx, which is the integral of x and negative 2 dx. And what does that equal?
Negative 1 over 3x cubed.
Negative 1 over x to the first. If I add 1, it's going to be negative 1, so it's negative x to negative 1 divided by negative 1, or just negative 1 over x, plus c. However, I know that when when x equals 1, my function equals 0. So if I plug in 0 and 1 for x, I now know that c has to equal 1. So the particular solution here is y equals, or capital F of x equals, whichever you prefer, negative 1 over x plus 1. Okay? And that's our particular solution. Okay?